little bit of a example, right? So I think he just posted it in the Moodle site. So if you go to the class Moodle, oh, hold on. It will be nice for you to be able to see it. Okay. So if you go to the class Moodle site, good. At the top of the page, you see this the final project proposal. Okay. And then at the end, you see this post for more ideas on graph algorithms, right? So click on that. And you see this project discussion, and then there's the graph topics.pdf. Click on that. You're going to see, hopefully, some slides. And so here's some background, and then we have some of these project sketch. Okay, so these are examples. And say, okay, you know what? Here are some potential projects, and it says, okay, here multiple set of intersection approaches are in the following slides. You can possibly come up with even more. And then which approaches are best under what kind of circumstances? So you can define a project like this and say, I want to understand all these different intersection methods and how under what circumstances are they better than one better than others. And you can even go farther and say, I'm going to try to figure out how to write a kernel, right? That would apply different intersection methods to different parts of the graph, depending on where the condition of the node that or the edge that that particular thread is processing, right? This is what we call the mega kernel, right? So you can have a kernel that implement all these things, and then you dispatch the code, right, according to the property of the edge or nodes that you're seeing. So that will be one project sketch, and then you can have another project sketch. There's sparse matrix, matrix approaches to triangle counting, and can you figure out how to specialize and use the GEM element-wise multiplications in a high-performance way for triangle counting, and how do they compare with let's say the methods that we use in the class, right? So that will be an interesting project as well. And then so Carl also gave you a little bit more information about that, right? So how you formulate these things, and he already talked about that in class. So don't feel too I would say too anxious about these things. Think about what you're interested in doing. Write up that brief proposal, and then we'll look at it and we'll give you feedback next week. And so I'm going to be traveling on Thursday, and but I'm going to go over these proposals with Wei and Carl, and then Carl will come on Thursday. We can do a kind of a group by group feedback kind of thing, so that everyone can get a better feeling about how to refine your proposal. So as I said, we just want you to turn in a reasonably thought out proposal so that it's a good starting point, and then you can evolve. Even 2 weeks into it, if you implement something and then you realize that it's too hard, right? Or it's too easy. Then come back, right? And we discuss it, and we'll help you to kind of adapt, right? So that's the nature of a lot of the industry project as well. A lot of times these teams work into something and then they say, it's way over our head. So then you pivot and do something different, right? So this is going to be pretty much the same. It's already confined in some way. So you're going to be either working on the graph algorithms, or you're going to be working on some training. A couple of groups already asked about the training. And then if you really want to work on your own research, write it up, and then we'll give you feedback. Okay. Any other questions? Any questions about the project before we go back into merge? A little bit less stressed, maybe. Right. I see the faces are slightly less tense. Right. Okay. So I'm pretty sure that all of you are going to have a good time. Working on. Make sure that you really work into it and try some new things and discuss what you find out with us. Okay. So we're going to continue with the merge thing. So slow. Look at this. No. What the heck? Okay. Here. Good. So before we continue, let's quickly review what we talked about last time. We talked about basic merge, right? The parallel merge. With the strategy that we talked about was that each thread is going to take a section of the C, which is the output, right? The output, and then say this thread is going to go and collect the elements that will go into that section, right? So we use the co-rank function, right, to find the section of A and the section of B, right? The section of A and the section of B that will need to come into this, into the C section. And so, that's the input identification. So the threads have to do some work to be able to figure out where in A and where in B it would be able to, we would need to look at, right? So that's the, that's actually the kind of the difficult part of these kind of merge algorithm. You don't really know where your inputs will come from until you kind of look into the data and then search around a little bit and then see, hey, this is the section of A and this is the section of B. Once you find those two sections, we use the co-rank function for the previous one and the co-rank function for the current one, and then we clamp them into these sections, and then we merge these two sections as using sequential merge algorithm. Right. So that was the approach that we taught. So we talked about this, co-rank function, and that was a sequential merge. And parallel merge. And Vikram was a little bit impatient here and asked, exactly how do we do it? But after the co-rank function, it should be clear that, for those of you who are old enough, I'm going to call Vikram grasshopper. And so if you don't know where that came from, you should go into the 70 TV series, and then so I'll give you extra credit if you find out which TV series has the grasshopper reference. Does anyone know?
Isn't it from the Teenage Mutant Ninja Turtles?
No, it's not Teenage Mutant. It's actually also very good, but it's not. The grasshopper reference. Okay, go find it. So So this is where we are. We have all these threads to go into A and go into B, and they're doing this n-ary search. Even though these n-ary, he's searching already. So so the n-ary search is very efficient, and it takes log n to find where the point that you want. However, at the beginning of the beginning of the strings or beginning of the data structure, you have very, very few places to search, right? And towards the end of a long list, you're going to have a large range of things to search. So if you have 1 million elements, the amount of work that you're going to do for the last section of C could be 20 times more than the beginning of the C, right? So you can still have this very uneven load or amount of work that these threads do, and those are not very good. The other one is, as they search, if you think about it, as they search, all these threads are going to be doing their own n-ary search. So who knows where they're accessing in A and in B, right? So they're not going to be coalesced, right? The accesses of neighboring threads are not going to be coalesced. So you have this kind of bad situation where the memory access is not coalesced, and you're creating a very big amount of memory traffic because the memory accesses are going to come back with cache lines, and then you're probably only touching one location of cache line. You bring in the cache line, and then you hop to another place because of the binary search, right? So these things will create very bad memory traffic. So you think about it and say, this is probably not going to be very high performance. So how can we improve the situation? The way that we typically could try to improve the situation is, one, maybe we reduce the number of threads that need to do the search, right? So if we can somehow reduce the amount of search, or another possibility is, let's do a search for a group of threads, okay? And then we take advantage of that search so that a group of threads can benefit from that search and then do small amount of work. So if we can do something like this, then we can reduce the sheer amount of memory traffic that we're going to create. We reduce the number of these kind of really random searches in the algorithm. And the second one is, if we can somehow confine the search that will be built on the initial search to be a small enough range, then we can potentially have the data in the shared memory. Because if the range is narrow enough, we can bring in the data into shared memory, and then do the search in shared memory. And whenever we do the search in shared memory, because the shared memory access don't need to be coalesced, we can actually get much faster access during the search process, right? So that's where this is a little bit different than the locality optimization or tile optimization for matrix multiplication. For matrix multiplication, what we're saying is we know what we're trying to access. So we bring in that data and we confine the access sequence so that everyone will be accessing those data elements, right? And then we focus those accesses in the shared memory, and then we move on so that we can eliminate most of the memory accesses. Here, we say that we don't know what we're accessing. Okay, I don't know where the threads are accessing their data. However, I know that I can have one representative thread that will sacrifice itself, do those kind of random search, but then the search result for that one is going to be used as a base for a whole group of threads. And those whole group of threads will be doing search in a much narrower range based on the first search result. And then we bring the data into the shared memory so that we can do the search in the shared memory rather than going out to the global memory. So that fundamentally is still using shared memory to eliminate as much of the global memory accesses as we can. But we need to first overcome that uncertainty, right? So that, let's see how we can overcome that uncertainty. So this is the basis of that the tiled merge kernel. So first of all, we're going to to define, instead of defining sections for individual threads, we're going to define sections of C for thread blocks. Okay, we're going to have much bigger sections, and each section is going to be covered by a thread block rather than a thread. Okay, so in general, you will see this kind of pattern in matrix multiplication, in these things. That in this case, we're partitioning work in terms of assigning a chunk of work to the entire thread block, right? So here we say, okay, we're going to have a cut out C in terms of big sections, and each section will be a subarray for a thread block. Okay. Now, at the beginning of the algorithm, what we're going to do is we're going to have one representative thread, okay, one representative thread in each thread block, okay, to do the co-rank function. So, but the co-rank function is going to be based on the current section, and the previous section. Okay, so we're still doing exactly the same thing, but it's just that we're using one representative thread to figure out the co-rank function for the entire thread block for the previous section and also for the current section, right? So it's not fundamentally different. So once we figure out those co-rank functions, then we know exactly a section of A, right? A section of A. That section is going to be bigger than the section that individual threads had in the previous version. A bigger section of A and the bigger section of B that will need to be merged, right? And we use the entire thread block to do that merge. Does that make sense? Okay. So what we're showing, I'm going to come back to to some of these, but each of these sections will be mapped into a section of A and section of B, and these things can be hundreds or thousands of elements. Okay. Because we need to have enough work for each thread block to do. Okay. So let's take a look at the outline. This thing is so slow. I need to reboot it. I'm going to call Microsoft the rebooting company. For this tiled kernel, we're going to divide the output into fixed length sections, and again, big number of elements, and assign them to thread blocks, right? And then each section should be at least a few thousand elements so that there's enough work, right, for each thread block to do. And each thread performs in the research identify actually a representative thread of each block. So I would change that. This is not each representative thread. Oh, there's a Cisco thing?
Yes.
Oh, here. Oh. Okay, Cisco is the rebooting company. Okay. Hopefully. So each represented thread performs the research for the entire thread block. And they still need to reboot.
I think I would be
Yeah, this is please check task manager and kill the top one.
Okay, let me just live with this one now, because if I ended up rebooting then I have to say quite a few jokes to for it to come back. So duplicate. Duplicate. Any good jokes?
I think it duplicated.
It's already duplicating, right?
Yeah.
And then, cool? Okay. So each representative thread will perform a n-ary search to identify the input sections for the entire block. And then the block will iteratively generate its output section. So this is the key. Okay. Now we know for each thread block, there are going to be maybe even a few thousand A and a few thousand B elements in a consecutive, tile, right? That should be used to merge into the C section, right? Oh, C section, that's interesting. So what we're going to do is like this. For that first section, we're going to see, we're going to have a long section here, and then we need to have, a section of A, a section of B to be merged into the same, right? So we say, we can actually load the first part of A and first part of B. So we can take a part of A and a part of B and load that into the shared memory. Okay, so that gives us the first part to be merged, right? So we're going to be generating the first part of C here, right? So depending on the value of the distribution of A and B, it could be that all the elements of A are bigger than all the elements of B. Could be. So in that case, B will have to come into the first part. And then we'll use up B, right? If we load the tile of B, then we need to reload the next elements, and we need to continue to do something like that, right? It could be mixture, right? It could be a mixture. We could have a few elements of A and a few elements of B to be used in that first part, and then we need to refill both A and B, right? So, but the bottom line is, if we have a big enough section of A and big enough section of B in each tile, then we can just treat this as a merge problem that the entire thread block would participate. So suddenly we can take this section of C, and divide that into smaller sections, just like what we did in the previous version, right? So we divide up the first tile of C into these small sections, and have every thread to do a co-rank function, right, on the portion that you already have in the shared memory now, right, in the shared memory, and find the beginning section and ending section for that little section, and each thread can now just do the merge, sequential merge on that. Does that make sense? Yes.
One thing that you mentioned about that each block will have its own representative thread.
Yeah.
Right, so it would do tasks that would be separate from the other threads?
No. They're just at the beginning. Right?
At the beginning.
Yeah, so when you enter the kernel, you say, if I'm the representative thread, I'm going to be doing a co-rank function for the entire section, for the entire big section, right? So that I can identify the beginning and ending part of that big A and big B. And once you have the co-rank function, then all the threads can now collaborate. Right?
But will this call like control divergence or something like that?
Yeah, yeah. At the beginning, it will be only one of them working.
So
but that's,
can you we could have like a separate log that's dedicated for this representative?
Unfortunately not, because you need to calculate the potentially. Oh, try it actually. Try it, because the idea is this. The idea is that thread is going to be doing that calculation, and then you will place the value into the shared memory, so that the rest of the threads can just use those values, and then calculate the next batch of C and the next batch of co-rank functions.
Next batch.
Right. So you need to make them available to the rest of the threads. But if you want to use let's say, an entire thread block, you could call a kernel. Okay, call a kernel, and then have let's say all the threads to calculate these big section co-rank functions, place them into the global memory, and then have the second kernel to pick it up. So my gut feeling is, the divergence may not be more costly than the kernel launch itself. So that's why I said maybe try it, right? But that trade-off is going to be like that, okay? And also you need to deposit the values into the global memory and for the second kernel to pick it up. Whereas here you can just calculate it and put it into shared memory for the rest of the threads to pick up, right? So those are the two additional costs, okay? So going back. So let's go back to the illustration here. So once we calculate, once we know that we loaded a tile of A and a tile of B into the shared memory, and we know that they need to merge into a section of C, right? So then basically this becomes a recursive definition of another merge problem. So then we can just say, this thing, even though it looks so small on the picture, these may be a few hundred elements. Okay, this may be a few hundred elements. This whole thing should be a few thousand elements, right? So for a few hundred elements and a few hundred elements here, you can actually have 256 threads to do to all collaborate, right? And each one will calculate the section and the co-rank function in these sections, and then they will merge those little sections into one of the C sections here. So after they're done, then you have some of these C, a tile of C sections complete. Then you move on to the next section of C. The next section of C is going to need to have also a tile of A and tile of B, but the data will be right immediately after the data that you have consumed in that first phase. So some of the data here will have been used in filling C, right? And this is where the inefficiency will be. Because remember, in order to fill a section here, let's say if I need to fill let's say 256 elements here, okay? I actually need to fetch 256 and 256 each from A and B. Because in the worst case, all the 256 could come from A, right? It depends on data distribution, I don't know, I have no idea. So in general, I will need to load twice the amount of data, right? From one from A, one from B, so that I can I'm guaranteed to have enough data to fill that 256 here. So now, after I finish this step, I'm going to go to the next section. Here's the thing. What do I do with the remaining elements that were not used in that first phase? Turns out that it's much easier just reload. Reload from the pointer that is left in that pointing to A, which points to this element, and then just load the entire thing. Otherwise, we'll have a third algorithm, okay? So we're going to start with a simple approach where we remember how many elements we consume in A and how many elements we consume in B so far. Then when we move to the next section of C, we will start with those positions in A and B and load another tile. Does that make sense? Okay. So this is the algorithm. So we come into the kernel, and then we use the we figure out the big section of C, right? These are the big partition of C for the block, and then for the representative thread, right? We use a representative thread for thread 0 in these blocks, and then we calculate the co-rank function for the big section, the previous big section and the current big section. So this gives us the beginning and end of A and B for this entire big section of C, right? So then we can, we can place the values into the shared memory, and then have the shared memory to so that all the threads will have access to these beginning and ending points. And then we would load, we'll say, okay, I'm going to the first load enough A and B to be able to fill the first tile of C. Okay, so we're going to iteratively go through this and fill all the smaller sections of C. So we'll do the tile loading. The tile loading is that we have the entire thread block. Okay, so let's say if we have 512 threads, then we define each section to be 512 elements, right? Each of these smaller sections to be 512. And so every thread would load an element, right? And then you will every thread will then go to a co-rank function, or we can do the quotient approach, right? So every thread can, let's say, be responsible for 4 elements. Then we need to load 1,024 elements, right? So we iterate 4 times, and then load the 1,024 of A and 1,024 of B, and we would fill 1,024 of C, right? So that's the first part. So we would have this iteration. The tiles I is 0 and I is less than tile size, and then so we would add the kind of the block dimension so that we can if it's the block dimension is 256 and tile size is 1,024, then we iterate 4 times, right? So that we can load all the threads, all the A elements. We load all the B elements we need for that tile, and then all the threads are going to calculate the co-rank function using the data in the shared memory, and then do the merge. Okay. So so now we use every thread to pick up a small section of C inside that tile, and then in this case, in our example, if the tile is 1,024, the thread block size is 256. We're going to have every thread to pick up 4 elements, and so then we calculate the C, the co-rank function for each of these little sections, right? Then that calculation is done in the shared memory now, right? So the vast majority of the co-rank functions will be done in the shared memory, right? And so you find the co-rank function, and then you generate you find all these kind of the sections pointer beginning and end pointers in the shared pointing into the shared memory, and then you do a merge sequential sort. You do a merge sequential sort. For that little section. So we're generating, every thread will be generating 4 elements of C, and then you're done with this current generation iteration, and then you move to the next tile, right? You move to the next tile of C, and then you do the same thing with A and B, and you keep track of how much you have consumed, so that when you go to the global memory, you load that tile from the consumed, the location after that consumed element, right? So then you're done. Okay, any questions? Here is a little bit of a problem. The problem is we are actually doubling the memory bandwidth consumption, right? So every time we load, let's say we fill 1,024 elements, we load 1,024 A elements and 1,024 B elements, and we end up using only half of them. And then we go to the memory, we reload, while some of the elements are still in the shared memory, right? So it would be nice for us to be able to reuse those elements already in the shared memory rather than trying to reload them from global memory. Make sense? And that actually is a lot more complicated than most people would think. Okay, so let's think about this. So we already kind of talked about this. then we talk about the pros and cons. The pros are coalesce loads of the input elements because we're not loading the tiles, right, into shared memory, and reduce global memory traffic for co-rank function access. And then we have coalesced stores if revised to generate output tile into the shared memory first. So when we fill the C, we actually write into the shared memory, right? And then all the threads can eventually collaborate to write into from the shared memory into C in the global memory. So all those accesses will now be coalesced. Great. The con is only half of the input elements that you load into the shared memory will be used. Okay, and you're wasting about half of the memory bandwidth. It's still going to be better. It's still going to be better than those random, co-rank function calculation and the random, the accesses into the, into the A and B, so it will still be better. So this goes into the whole thing about circular buffers. Okay, so if you think about it, we have a tile of A and tile of B, and after every step, we're going to have half of the elements not used. But we don't know how much of the half will be in A and how much of the half will be in B. So they can be any kind of combination, right? So that's kind of the annoying part. So what we should do is this. We take whatever is remaining in that shared memory for A and B, and then we just refill whatever it takes to to refill the buffer. However, we have a situation where the buffer, after the first iteration, we consume all these elements. So when we refill, these are still elements that we're going to be using. So when we refill, we need to refill into this, right? So, and then when we calculate the co-rank function, we will need to have to write back. And the co-rank function, the way that we define it, is based on consecutive locations, right? So we're doing binary search. Remember the binary search thing? So if we have a situation where the data is actually wrapped around, we need to redefine the binary search in order to be able to tolerate this kind of wraparound. So instead of trying to write a new binary search algorithm with this wraparound buffer, what we can do is we can still use a virtual binary search algorithm that conceptually is searching a sequential space, but then underneath we handle the indices with the wraparound to hide the fact from the binary search algorithm. So otherwise, it will be extremely hard to verify your binary search. In fact, some of the students in the past tried to directly write a binary search algorithm based on these kind of wraparound buffers, and there was endless confusion, right? So what I'm going to present today is going to be the binary search algorithm is still going to be conceptually based on just pure consecutive locations, and then you have an implementation of the co-rank function implementation that will be that will use the underlying modulo operations to hide that complexity from the high-level search algorithm. So this is how the circular buffer works. So after the first you start, and then after the first step, exactly what I shown in the blackboard, we're going to have some leftover elements. So we're going to need to refill for those elements, right? And then we're going to have to consume from here to here, and then at some point, this will be the next consumed element, and then you need to refill, from here to on, right? So the consumed elements are here, so you need to refill and fill you need to refill based on the consumed element and on. So you have this wrap around, right? So this is what we're showing here, okay? So now you have to keep track of, not just the, the consumed elements in the global memory. You also need to keep track of the consumed location in the shared memory, right? So that's why we have consumed and consumed. We have the B consumed, and also we have the BS consumed. So this is the consumed location in the shared memory. So you need to keep track of, where you're going to start the refill in the shared memory, right? And also how many elements to refill, right, from A and for B, right? You need to know the beginning location and how many elements to refill in each of the buffers, right? So that's the BS consumed and so on. So when we refill, we still will use the threads. The threads, according to their thread ID, right? We're going to use consecutive threads to fetch from the global memory, but not all the threads need to be activated anymore, right? Between A and B, right? Between A and B, well, we're only going to need to have, part of the threads to refill A and part of the threads to refill B. And that's exactly the reduction of memory bandwidth consumption, right? We no longer need to fill twice the amount of data of the C section. So this is, these are the calculations. In fact, this is the part that is worth reading the textbook. I spent several days writing that part in the textbook. So, so that you will see how this is the beginning. This is the beginning part of the. This is the where the tile starts, and then this is the amount of data that has been consumed, subtracted from the tile size. So this is the refill position, and then this defines the beginning location, and then you have I plus thread index into the into the to do the refill, but then you need to do the modulo of the tile size to wrap it back, right? So that this whole thing gives you the index into the shared memory. So you're going to say, what the heck? You have so many, you're doing all these work just to be able to write an element into the shared memory. Turns out that the cost of global memory access is so high. All these things are still worth it, right? So this is the recent trend about computing. Because the memory accesses are so expensive, people can do all kinds of extra computation and so on just to save memory bandwidth and still get much better performance. Okay, yes?
Would that be easier if we just do memory, like move in the shared memory?
Yeah.
Like for the
Yeah.
unused thing,
Yeah.
you just add it
Potentially.
to the head and
Yeah.
do that.
Yeah. So if you move the memory, you still need to calculate because you still need to know where
Yes.
it begins, right?
Yes.
Yeah.
You
So exactly right. So if you always make sure that the next tile always starts from the beginning location,
Yes.
then all you need to do is to figure out the consumed position,
Yes.
and then you move the whole thing to the front. But then you need to load from this position here from the global memory.
Yeah.
Yes, it's possible to do that. Okay, so that's another version. In fact, I was going to tell everyone you should try that version. Yeah.
That sounds like
Maybe not. So try it because there's some trade-offs. As soon as you implement it, you'll start to see some trade-off. It's an interesting experiment, right? Okay.
So can we use like constant memory in this scenario and because it's highly cached?
Yeah. Okay. The question is, can we use constant memory or the texture memory, for this kind of access? So it turns out that you know, if you use the original algorithm, or even you know, when you are you know, doing the first phase of those kind of random you know random code rank function access for the representative threads, it may be helpful to use the texture memory. Texture memory. The problem with constant memory is that the constant memory size is very, very limited. Okay, so be careful with that. And so, but the newer GPUs now, you know, they are supposed to be able to just map any of the variables that you say is not going to change. In this case, A and B. Okay, and you know, into you know, cacheable, right?
Yeah.
So. But still, I think you still get better performance by doing, you know, the texture mapping, and then you should still be able to get better performance.
The texture memory is larger?
Texture cache, the texture memory, you know, is actually funny. It's not clear exactly what the size limitations are, but it's the texture mapping, you know, the texture filter cache that has a lot less constraint than the constant memory cache constraint. The design of the cache are different.
Right.
Okay, yeah. Good. So, where are we? So, what we're going to do in this algorithm is that, you know, remember we have this wraparound thing, you know, so the ASS is going to start, and then, you know, the data is going to wrap around. But when we write the co-rank function, we're going to have a virtual view, okay, simplified view, where we're going to start here, but we're going to effectively project an image that the data is going to just continue. Okay, so it's this whole data is going to be in consecutive locations, okay, and be the same way. So then we can, you know, design a kernel. Okay, so when we write a kernel, we can just write a kernel based on that simplified view. Okay, so we come in and you know, we do the thread. So this is the thread ID. You know, so we do the kind of the for each thread, and then we find the co-rank function for C current and C next. So when we pass the information into the co-rank, you know, the co-rank function, we're going to just let the kernel programmer assume that these co-rank functions are going to be operating on consecutive locations. So we're going to pass the parameters into the co-rank function essentially into the shared memory exactly the same way that we pass the global memory locations into the shared memory. Okay. So from the kernel point of view, there's nothing different except that we're doing the co-rank function in the shared memory, not in the global memory. Okay. And then once you get the co-rank function, you can do the merge sequential, you know, code. And this merge sequential, from the kernel point of view, you're also merging a sequential section of A, sequential section of B in the shared memory, and merge that into a section of C. However, in the implementation of these functions, it's going to manipulate all those modulo operations so that they will actually generate the correct co-rank function values of A and B. And in fact, those co-rank functions values will come back sometimes reversed, right? Because, you know, when you have a modulo situation, the later section pointer could be before, right? It got wrapped around. So these function, these co-rank function values are actually coming back as sequential function values. But then in these merge functions, it needs to interpret those with the modulo formula, right? So if you do that right, yeah, this is just the rest of the kernel, and then let's take a look at the co-rank function. the corank function is not the corank circular. Remember, these values are passed in as if they are consecutive locations, right? So the reality, this corank function you need to deal with is actually that buffer is actually a circular buffer. So we have the I and j still, I and j and I low and j low. Remember that the binary search, right? So in each iteration, remember we adjust where the windows are and also we shrink the window, right, in the binary search. So we divide by 2, so this is the binary search. And then once we get into the, the real search, we generate a I circular. So this is the wraparound I, right? So we take the value here, and then we either do the AS star plus I, or we do the plus I minus the tile size, because before we go and actually access the value in the A buffer and the B buffer, we have to convert the virtual index into the real index so that we can find the value, the correct value in the buffer. The values are the ones that we look at to determine if A minus 1 is less than Bj, right? Remember that? And then AI has to be also less than the Bj minus 1 plus 1, right? So we need to maintain those properties, but the I minus 1, J, I, J plus 1, all these values will eventually need to do the wraparound the transformation to be able to access the correct values to make those comparisons, right? So if once you understand that, you will see that all the manipulations are still going to be I and J, except when you go and try to access the A value and B value to determine your binary search convergence. When you access the data, you convert that into the modulo value and then access the right value. So that's why we only need to generate this I circulate and I minus 1 circulate, J circulate, and J minus 1 circulate, when we actually need to go and access these A and B values. Okay, and so those are, you can see that A is accessed by I minus 1 circular, right? So that's, that's where the conversions are. So we can largely still use the original corank function and also the merge, the sequential merge, as if they are sequential. But then when we go and access the real values, we actually do this wraparound modulo operation, right? And as long as you keep that straight, it's actually very, very easy to write the code. And as we, Shimi?
Yes.
Sumi? Okay. As Sumi mentioned correctly, if we spend the cost of always shifting A and B to the beginning, the remaining part of A and B to the beginning, then we can just refill, towards the end, and then we can always assume that I and J are going to be operating on sequential locations. Then we don't need to do the modulo transformation. So it's really about whether it's worthwhile to do these additional, some of these additional minus tile size computation before you access the A array, versus taking some time to actually move the data, right? So it will be a kind of interesting experiment to do. For the sequential merge, it's the same thing, because the original sequential merge function is taking two consecutive sections of A and B, and then you're kind of taking the locations, comparing, and then writing into C. So you can still use the same thing, but when you try to really access the A element or B element, you use the circular, circular version, and then access the value, and that's it. Okay. So that gives us the end. Okay. So we start with a merge pattern. We say, okay, it was not that clear how we can parallelize this thing. And I say, okay, So if I'm willing to partition the output, right? Partition the output into these sections, and then we can have all these threads to go and collect and gather the data. But it's not a trivial gather because we need to have a co-rank function in order to identify the section. And basically the trick is we do a very, very quick search and then see where the section should start and where the section should end. And that's, that gives us those, the little sections of A and B that can be used by this particular thread to generate that section of C. And then we say, okay, the memory access patterns are terrible. And during that binary search, and we really don't want to do binary search that in global memory. So we say, okay, so let's figure out if we can do a tiled approach. And indeed, we can do a big tile. Okay, we can do a big tile, and then the big tile is going to be able to we can stream the big tile into the shared memory, and then for every small part of the tile, we'll have a big section, and then we can do tile by tile filling of C, and each tile can be partitioned into small sections, and then we use the binary search. And this has a very, very nice side effect, because when we confine the binary search in a tile of A and tile of B, we bound the number of elements that the binary search has to do. So the variation now becomes a lot smaller, isn't it? So we got rid of the load imbalancing problem. We confine the load imbalancing problem to a few threads at the beginning of the kernel execution. Okay? So that's the last point I wanted to make. Okay. Any questions? Yes.
So I want to talk about before the tile method, we have multiple threads that divided the output into sections, and
Yeah.
each one had to find the markers for the start and the end, right?
Yes.
So the thing is that for two consecutive sections,
Yeah.
the end and the start would be the same, right?
Yes.
So my thinking is if we're gonna use some shared memory, and
Yeah.
if the first thread finds the end first before the second thread finds
Yeah.
its beginning, it
Yeah.
should some way inform
Yes.
it through
Yeah.
somehow.
Yeah, you can potentially save some computation. Absolutely right. However, you need to do the same thread. So did you notice? I was hoping that someone would ask this question. So if you look at the tile algorithm, we'll just use this one. Okay, loading tiles. So when we do so this is the same thread that we need to do when we put when we load the tiles. So if you try to eliminate the use the calculation of the second one, then you will need to add another sync thread,
Right.
right?
But if you use some shared memory, and
Yeah.
we have some bit reserved, we do one to inform the other thread. If
Yeah.
you look at now the output
Yeah.
is ready, and then
That may be even more expensive.
Right.
Within the thread block, I would still just use the sync thread.
right.
Okay. Any other questions? Yes.
Yeah, so this assumes merge sort because we're doing merge. A and B are sorted already.
Yes.
And this would work very well if we started with one element in each A and B and then
Yeah.
just recursively do merge
Yeah.
up till you're done with the whole list. But
Yes.
how would we go about, what would be a great algorithm for in GPUs to do sorting of A and B itself as opposed to just doing merge from starting with one element in A and B?
Yeah. So the typical way of doing this thing is actually, I'm only giving you the merge part. This is a great question. So what really happens in real software is that let's say you take a very long unsorted list, and then you just partition them into sections, and then you use threads to sort them sequentially,
Sequentially, okay.
and then you make those sections small enough
Right.
that you ended up with the kind of the small sorted sets,
Of A and B.
and then you do the merge,
Merge.
right? So they also then you essentially you would be doing a binary merge,
Right, exactly, right.
right? So each of these binary merge is one of these.
Right, right.
So basically, you're gonna have to have like multiple levels of that merge tree. Eventually, you get the
So
full-
basically, doing the sort like in a smaller section per thread sequentially is
Yeah.
the
Yeah.
ideal
Yeah.
thing to do.
And then the rest is just all
merge.
all merge
Right,
pattern.
right. That's
Exactly right. Okay. Any other questions? So if you're interested in all these search kind of things, sort kind of things, you should also take a look at radix sort, because the what we're talking about here is what we call the sort that actually involve physical movement, data movement. But you can also have in-place sort, and in-place sort based on radix sorting, and that's actually really fast on GPUs. So, but it's one of those things that are special purpose. So in radix sort, you have to have a very narrow range of values that these things can have. So, but if you're really interested in sorting, you should go to literature and read